Application of Tukey's test for statistical measurement of percentage indexes derived from the difference between predicted crystallographic data in 5 Nitihf alloys obtained by 2 processes. Abstract: the present paper uses the Tukey test to measure the minimal significative difference, MSD, between crystallographic data predicted by nonlinear mathematical models generated from graphics published by Zarinejad, 2008, and Potapov, 1997, on 5 nominal compositions of Ni50Ti50XHFX. At percent substitutional alloys fused by arc melting and melt spinning processes. Results show that the calculated MSD do not represent a statistically significant difference. Therefore, it is concluded that the independent variable, hafnium content, does not change the analyzed dependent variables, lattice parameters, crystalline structure volume and monoclinic angle SS, for any fusing processes. Keywords: ANOVA, monoclinic, Nitihf, statistical test, Tukey. Introduction. The production of shape memory effect, SME, alloys depends sensibly on particular processes that, based on the variation of parameters involved in the equipment used, maximum melting temperature, vacuum magnitude, purge intensity, purity of the metallic charges, torch exposition time, etc., can or cannot generate different crystallographic features for samples which theoretically have the same chemical compositions. In this sense, it is important to compare the obtained results through predictive modeling functions to observe whether there are any significant statistical difference capable of indicating a great variability in crystallographic characteristics, such as lattice parameters, ABCA, cell volume, vol A3, and characteristic angle SS, beta O, of the monoclinic structure, space group P121/M1. In this work, they are studied as variables dependent on hafnium content, which is considered an independent variable in the nominal composition. The focus of the study is on room temperature B19 Martensitic phase B19, which has a monoclinic structure, Pearson symbol MP8, and is considered by the literature as an unstable phase. In addition, the 5 substitutional compositions Ni50Ti50XHFX. At percent considered in this instance are x equals 8, 11, 14, 17, and 20. At percent, which were obtained by 2 different processes, arc melting, Zarinejad, 2008, 1 and melt spinning, Potapov, 1997, 2. Prediction of the B19 phase of Ni50Ti50XHFX. At percent alloys. Based on the graphs by Zarinejad, 2008, 1, which measurements were obtained by XRD3 refinement method, it was possible to calculate, through numerical proportions, the equivalence of the lattice parameters, A, B, C, volume of the monoclinic structure B19 and axial angle SS, as shown in Table 1. From the obtained results, the same variables were estimated for the 5 alloys of study, x equals 8, 11, 14, 17 times 10 to the power of 20th at percent. From the third-order nonlinear regression, shown in Figure 1, it was adopted the polynomial function y equals ss0 plus ss1x plus ss2x2 plus ss3x3 plus or minus. For each parameter, which resulted in y equals 2,77219 plus 0,00562x plus 0,00104x2, 2,73732e5x3, R2 equals 1, YB equals 4,30224, 0,04354x plus 0,00354x2, 9,94737e5x3, R2 equals 1, and EQ equals 4,52671 plus 0,03934x, 0,00287x2 plus 8,85679e5x3, R2 equals 1. The determination coefficient R2 are equal to 1. This indicates that the proposed models are suitable to describe the phenomenon in which the parameters A and C increase, while the parameter B decreases. Equally, the models adopted for volume and SS angle for B19 phase presented 100% fitting. Figure 1. Figure 1, scatter diagrams and cubic regression curves, with the values of lattice parameters, A, B, C, determined for the Ni50 Ti50 XHFX. Alloys proposed by Zarinejad, 2008. All the values estimated for the 5 dependent variables are organized in Table 2. A comparison between the values of Table 1 and Table 2, confirms a coherence in the direct proportion between the percentage of hafnium and the volume of the monoclinic structure, phase B19. The lattice parameters for the 5 Ni50 Ti50 XHFX. Ni-rich alloys of study are plotted in Figure 2. Figure 2. Figure 2, scatter plot with estimated values of the lattice parameters of the crystal structure B19 in Ni50 Ti50 XHFX. Alloys, X equals 8, 11, 14, 17, 20%. According to Figure 3, A, from the regressive function YB reg equals 54,31119, 0,25944x plus 0,05413x2, 0,00137x3, R2 equals 1, adopted for all 4 Zarinejad, 2008, alloys, in which x equals 5, 10, 15 times 10 to the power of 20th%, it is possible to predict the volume, A3, of the B19 monoclinic Martensitic structure for the 5 compositions of the alloy Ni50 Ti50 XHFX%, x equals 8, 11, 14, 17, and 20%, shown in Figure 3, b. Similarly, using the cubic polynomial function YSS equals 98,02467, 0,03662x plus 0,00981x2, 1,46128e4x3, R2 equals 1, adopted for Zarinejad alloys, 2008, as seen in Figure 4, A. The SS angles of the B19 phase for the 5 Ni50 Ti50 XHFX%, HF equals 8, 11, 14, 17 times 10 to the power of 20th%, alloys of study were predicted and plotted in Figure 4, b. Figure 3. Figure 3, nonlinear regression, order 3, from which the volumes of the Martensite phase, B19, of the 5 substitutive Ni50 Ti50 XHFX. X equals 8, 11, 14, 17, and 20%. Alloys were calculated. Figure 4. Figure 4, nonlinear cubic regression from which the SS angles of the B19 Martensitic phases were estimated for the 5 Ni50 Ti50 XHFX. X equals 8, 11, 14, 17, and 20%, alloys rich in nickel. For the functions used as statistical models, it was calculated the analysis of variance in each polynomial, according to Table 3. Table 3, ANOVA is calculated for each model y equals SS0 plus SS1x plus SS2x2 plus SS3x3, referring to the 5 variables of the B19 Martensitic phase of the 5 Ni50 Ti50 XHFX% alloys. To make explicit the coherence of the regressive model adopted for the volume, the calculated volume, vol equals A.B.C.sense, was added in Table 3, on top of which the model YB-calc equals 53,5806847 plus 0,018979973x plus 0,033586976x2 plus 8,39734e04x3, R2 equals 1, was created. All of the R2 values were equal to 1. This makes unnecessary the calculation of adjusted R2, normally used to measure the real degree of modeling reliability. According to Table 3, since there was no standard error in the coefficients, the general error of the models is 0. For this reason, F value is not presented in Table 3. Thus, it can be stated that the mathematical models adopted here are statistically significant as well as predictive for all 5 dependent variables observed. Taking the 4 Zarinejad alloys, 2008, as a reference, the residues found for each regression, in each variable of the monoclinic structure B19, are presented in Table 4 and Figure 5. Table 4, residues of each variable calculated for phase B19 of the 4 substitutive Ni50 Ti50 xHfx. At percent, x equals 5, 10, 15, and 20, alloys from Zarinejad, 2008. Figure 5. Figure 5, dispersive plot of residues in each variable of the B19 monoclinic structure, A, B, C, volume and beta SS, O, for the 4 alloys of Zarinejad, 2008. 3. Prediction of the phase B19 on Ni50 Ti50 xHfx. At percent ribbons quickly solidified by melt spinning. Based on the Potapov plots, 1997, for the 6 ribbons of substitutional compositions Ni49.8 Ti50.2 xHfx. At percent, x equals 8, 9.5, 11, 15, 20 times 10 to the power of 25th. At percent, obtained by melt spinning, the calculation of lattice parameters, A, B, C, B19 monoclinic crystal volume and characteristic angle SS are shown in Table 5. Table 5, crystallographic characteristics of the Martensitic phase obtained by XRT refinement for the 6 ribbons with Potapov, 1997, nominal compositions Ni49.8 Ti50.2 xHfx. At percent obtained by fast melt spinning solidification. Considering the similarity of the composition used by Potapov, 1997, regarding the composition Ni50 Ti50 xHfx. At percent, adopted in this work, difference of 0,2. At percent in the contents of NIETI, the values of Table 5 were used to proportionally calculate the same variables having as reference an alloy rich in Ni of nominal composition Ni50 Ti50 xHfx. At percent, quickly solidified by melt spinning. The results are shown in Table 6. Table 6, crystallographic characteristics of the Martensitic phase calculated proportionally from Potapov's ribbons Ni49.8 Ti50.2 xHfx. At percent, 1997, for the theoretical ribbons Ni50 Ti50 xHfx. At percent, x equals 8, 9.5, 11, 15, 20, and 25. At percent, obtained by fast melt spinning solidification. Based on the data in Table 6, these 5 variables were calculated with the nonlinear cubic model, which is composed by the third-order function, equals 0 plus 1, plus 2, 2 plus 3, 3 plus, equals 1, 2. The values of R2 are, for the dependent variables A, B, C, volume and SS, respectively, 0.9986, 0.9938, 0.9987, 0.9986 and 0.9885. This certifies a large percentage of correct answers. The estimated quantities for the 5 compositions are presented in Table 7. Table 7, estimative of the crystallographic characteristics of the B19 phase in the 5 ribbons quickly solidified by melt spinning for the composition Ni50 Ti50 xHfx. At percent, 8 to 20. At percent. Using the matrix adopted for monoclinic crystals for, according to the equation 0,1, the volumes were recalculated to show the coherence of the statistical model. The volumes found were, for the 5 compositions, HF equals 8, 11, 14, 17, and 20. At percent, in this order, 57.135351818A3, 57.85901627A3, 58.51514303A3, 59.10615326A3 59.63533041A3. The model functions were determined based on the coefficients listed in Table 8, accompanied by the respective errors. For each of the cubic functions, the values of adjusted R2 computed are, in the decrescent order, in Table 8, 0.99643, 0.98445, 0.99682, 0.99658E 0.97115. Figure 6. Figure 6, left column presents the graphs with estimated values for the 6 Potapov ribbons, 1997, and right column shows the calculated values for the 5 theoretical ribbons of nominal compositions Ni50 Ti50 xHFX. For a graphic visualization, Figure 6 presents the values calculated for the 6 Potapov ribbons, 1997, plotted in the left column, Figure 6a, Figure 6c, and Figure 6e, in a way that they are compared with the values predicted for the 5 ribbons studied here, plotted in the right column, Figure 6b, Figure 6d, and Figure 6f. According to the obtained numbers, the values of SS angle, volume, and A and C are directly proportional to the atomic percentage of hafnium from the alloy, except in the lattice parameter B, which is inversely proportional to the content of HF. At percent. 4. Comparison of crystallographic characteristics of the Martensitic phase in Zarinejad's alloys and Potapov's ribbons. Due to the fact that these variables are different, i.e., one-dimensional, lattice parameters, two-dimensional, SS angles, and three-dimensional, monoclinic structures volumes, entities. To enable a dimensionless comparison between the predicted data from Zarinejad, 2008, and Potapov, 1997, it was necessary to consider the percentage indexes of the differences between the estimated values for each parameter, A, B, C, vol ESS, of the 5 compositions Ni50 Ti50 xHFX. At percent. This makes them arbitrary data. Therefore, it was necessary to organize the sample series from Table 11 with the dimensionless format of Table 9. Percentage indices have arbitrary units. Using descriptive statistics, the measures of central tendency and dispersion were summarized in Table 10. The normal distribution, differences percentage indexes versus X indexes density, is represented by equation 2 and plotted in Figure 7. It is composed of S, standard deviation, E, constant de Euler-Mascheroni, 2.718, P, proportion, and population mean. Percentage. However, there is a clear comprehension that the crystallographic characteristics depend not only on the hafnium content, but they are also sensitive to the peculiarities of the 2 production processes as well as the typical variables of each one of them, electric arc melting, and quick solidification melt spinning. Figure 7. Figure 7, plot of the probability curve, 100 points, of the difference indexes estimated by the statistical models adopted for Zarinejad alloys, 2008, and Potapov ribbons, 1997. Depending on how the peculiarities involving each one of the processes are treated, one can directly influence the main properties of the samples such as homogeneity, amount of residual stress and minimization of oxidation, among others. These physical and mechanic properties, among others, are derived from atomic arrangement known as crystallographic structures, or crystalline structures. It can be mentioned as variables of these processes: the number of times that the bulk was melted, exposure time to the torch, type of material of the mold, efficiency of the applied vacuum, rotating speed of the copper flywheel in quickly solidified ribbons, etc. Hence, all the possibilities of variation and instrumental errors generate conditions of solidification which interfere in the microstructure of the alloys and obtained ribbons. V. Conclusions. The analysis of variance, ANOVA, is an unilateral test based on the F-Snedeker table, which after calculating the F value, it measures whether it is inside or outside of the acceptance area, according to the following hypothesis test. As it is an one-way ANOVA, the only factor, independent variable, is the atomic percentage of HF. At percent. As a rule, in terms of null hypothesis, H0, the calculated F value is inside the area of acceptance, i.e., minor than critical F. Otherwise, if H0 is rejected, the alternative hypothesis, H1, will be accepted, having necessarily the F value calculated outside the area of acceptance, i.e., bigger than the critical F. In this case, we considered that F, 5%, dF1, dFW, df2, dfr, equals 3,12, tabulated, according to the standard table for Tukey's test, a equals 0.055. According to table 12, as the calculated f equals 3.13 is bigger than the critical tabulated value, we concluded that there is a difference between the averages of both treatment groups, Potapov and Zarinejad. This conclusion is also confirmed by the p-value, which is smaller than 0.05. The lower the p-value, lower is the possibility for H0 be true. It is important to note that df1 horizontal equals numerator is the degree of freedom between groups, dfw, and that df2 vertical equals denominator is the degree of freedom of the residues, dfr. Table 12, one-way ANOVA calculated for two series of samples of the crystalline dimensions of the B19 monoclinic phase in Ni50 Ti50 XHFX. At percent alloys and ribbons obtained by conventional and rapid solidifications, Zarinejad and Potapov, respectively. 1. Between groups, W, equals treatment equals between treatments equals between. 2. Within groups, R, equals residue equals error equals within. 3. df equals degree of freedom. Therefore, the null hypothesis is rejected, H0. However, to ascertain whether this difference is statistically significant, it is necessary to perform a parametric test to certify the significance. This decision was taken based on the normality test of Anderson-Darling 6, which predicts as normal the set of 25 data organized in Table 9, as shown in Figure 8. Figure 8. Figure 8, Anderson-Darling normality test for the percentage indexes. A comparative analysis was made between two different solidification methods, arc melting e-melt spin, when applying the Tukey's test, through Table 13, 7.2, in a complementary form to ANOVA, calculate the minimum significant difference, MSD, there is between the averages in the Martensitic crystallographic characteristics, according to the original dimensional data predicted by the adjustment models, shown in Table 2 and Table 7. It is concluded that the method to obtain the alloys doesn't interfere in the dimensions here evaluated, that is, there is no significant statistical difference. This is due to the fact that the calculated difference, dash, was of 0.75. According to equation 3, the m.s.d. necessary for both groups, data series, to have a significant difference is 19.027. 03. In this calculation, QQ, 5%, K, df of residues equals 2.899943 is a tabulated value, F's Nitihf table, A equals 0.05, the QMR is 1076.22, highlighted in Table 12, and the number of repetitions is equal to 25. This count of 25 is contained in Table 13, before the summary, resume.